Next speaker is Garth Illingworth from University of Santa Cruz.
Good. Thank you very much. Good morning, everybody. Yeah, okay, sure. Yeah, let me know. I tend to keep talking. So what I would like to do is talk a little about JWST in its first year and give a little background, and then just highlight some of the things that have struck me scientifically over the last year that's come out of this. And so I think it was only a year ago when a year and a couple of weeks, that we saw these first images. This one was shown at the White House on the Monday night, and it was a spectacular image. And it was interesting, actually, that when I first looked at this, I thought, this is magnificent. But it's sort of like deja vu. I mean, we'd all seen this from the Hubble Frontier Fields. And so then I realized that first there was a goal here with this particular one. It was really to show that we were on the path to meeting our goal of first light, first galaxies. And the thing that really blew me away once I thought about this for a second or two was, this is 12 hours. We spent hundreds of orbits with Hubble doing these fields, and in 12 hours we had an image that had more science content than any of the Hubble Frontier Fields images. So I thought, yep, it's on its way. So what I would like to do here is give you a little background about how the science case for Webb developed. I've talked at various points, as one of them here, about the political and the technical aspects of developing Webb. And I wanted to focus on the science case this particular time. And so, just as an introduction though, this actually all started about 35 years ago with this comment to me: start working on the next big mission. It will take a very long time. And this was Riccardo Giacconi at the Space Telescope Science Institute. He was a director. Deputy director, one morning he came in and told me this, and I went, Riccardo, we've got years and years of work on Hubble, and you want us to actually work on the next one? And after thinking about it, talking some more, talking to other folks, we realized, of course, he's right, and Tui was the boss, so it was, yes, sir. So a small group of us got together, Peter Stockman, Pierre Boully, Chris Burrows, and really started thinking about what we would try to put together for the next generation. What really excited us was this concept of a really cold, really big infrared space telescope in orbit far from Earth. These are the folks that are involved there, and a big group of people all working Hubble in the mid-'80s at Space Telescope Science Institute. I even had hair color at that point. That's slightly changed over the years. But it was a great time to be there in many ways. It was tough but very exciting. But on this particular aspect, what was the challenge was that we were conceptualizing what came beyond Hubble before Hubble. We all knew Hubble was going to be transformational, and then we wanted to do something transformational beyond transformational. It's a little challenging. And so you just do what you can. You get together with a bunch of good people and you talk about things. Angel and Wolf had already been talking about searching for Earth-like planets with a 16-meter cold telescope for a couple of years. We'd talked about distant galaxies. And David Koo reminded me when he was there in one of the many coffee discussions that we had talked about measuring 3D motions of galaxies in Virgo using a telescope like this. So there were lots of science ideas, but one of the key things was you wanted a telescope that would open up the discovery space dramatically as well. And so that was a very important factor also. So I went back and I was trying to find where we first enunciated a lot of the science points. It was a talk what I could find was a talk that I gave at the IAU in 1988, where we were talking about the mission, but also about the science. Next page. But I do really want to note that the folks like Roger Angel, Peter Stockman, Pierre Boully, Riccardo, and many others all played a major role in actually helping us frame this science case. And so it was interesting that even then, before Hubble, and we were in our infancy with working distant galaxies, radio galaxies, QSOs were the sort of things that were popping up at, quote, high redshift greater than 1, but essentially no galaxies were known around that time. David Koo was working on this stuff, and back in then too, Tony Tyson. But it was a small community, very limited data sets. But already we were talking about distant galaxies beyond redshift 1 as a key part of it. And of course, interestingly, the Earth-like planet aspect. This was years and years before exoplanets were discovered. So when we came to this 1989 workshop, we collected a bunch of people to talk about science goals. And as you look through that, these are goals in areas that we're still interested in, for sure. And so the framework developed, and particularly, NGST and distant galaxies, with Jim Gunn talking about that, and then Roger Angel about Earth-like planets. These were sort of the two that, I would say, two legs of the chair, as it were, that helped frame the science case in a way that a lot of people could resonate with. Then in the panel in the decadal survey, again, we had to and wanted to develop the science case further, and we did, particularly with the Earth-like planet aspect, with the distant galaxies, and the discovery aspect popped out as well, of course, with this recognition that we were going to be in a regime where the background was hugely less. And so, as this next one, so here we are, 10 to the 7th times less. So this is by itself an indication of the discovery space is going to be huge when you get a change in the background like that. And of course, infrared was absolutely in its infancy. At this time, we were talking about putting together a few detectors to make a multi-channel detector, a few individual devices in the infrared. But we knew the future was, there were great opportunities coming up on the 10, 20-year time scale, just as there was with the expanding visible light detector field. And so that new technology plus this gain in space was what really opened up the discovery space for us. Then, of course, in the middle of the 90s, this image was taken. Bob Williams decided he was going to do it regardless of what his advisory committee told him. Sandy and I were on this. I think we supported it, but there were a number of people on that committee who did not support it. But Bob thought, to hell with you all, I'm going to do this anyway. And did. 10 days on Hubble, and lo and behold, this popped up with an amazing sample of galaxies. 6 or 7 hours on Webb. That's pretty impressive. So then, in the latter part of the middle of that decade and on, there were three major activities that really framed the science and were very important for this mission. There's a lot of words here. I just highlighted in red again. In every one of these, distant galaxies played a central role in defining what this telescope was going to be scientifically. And to the extent that every one of these also had the Hubble Deep Field on the cover. And so at that point, we had in many ways the core science, but also we needed to make sure that as we're selling this to a broad science community, that an observatory really could do a wide range of science, almost anything that folks were interested in. And of course, like Hubble, you come to a telescope like this, it's certainly the case. And the discovery potential was huge here with this 10 to the 7th gain, small PSF from being a big instrument, a big telescope, and the upcoming detector technology. But crucially, what we really needed to sell this in a very different environment, say in Congress or Washington, was that we needed to be able to get to the policymakers all across Washington, the OMB, OSTP, OMB, everywhere. Within NASA, of course, there were people there who recognized it, but a lot of people did not. You needed to filter that up to the 9th floor, to the administrator's office, get it to the media. You need something very succinct. And so that's what this elevator speech is. And of course, you probably know that this is sort of came about. If you get into an elevator with somebody important who could influence your budget or the choice of what you do, and they say, what are you doing? You want to say, within between floors, what it is you're doing in a way that's memorable. And here we would just say, we plan to build a telescope that will find the first galaxies. First slide. Something very succinct that's memorable, that you want them to carry away, shorter than a tweet or whatever Elon now calls his latest thing. So anyway, by the early 2000s, we had set a framework scientifically which pretty much remained in place for the next 2 decades. So, as you've seen all this many times in many talks. So it was interesting, actually, as you look at what I've just showed you, that the broad science goals actually have not changed hugely over decades, though the details have clearly changed. We have learned a lot. So last July, a year ago, we got to this point where we saw all these images and realized we had an amazing telescope. And what was interesting from distant galaxy perspective was less than a week after that, there were two papers, these two from Nadeau and Castellano, on finding a galaxy, a very luminous galaxy, even further away than GNZ 11, the galaxy that was the most distant one, well, actually the second most distant with Hubble. That's an interesting story in its own right. So these two papers came out, and I think there was just a recognition that, well, this is going to really change the game. And it did. So, whoops, wrong way. So within weeks, there was a huge effort here with a large number of papers with very high redshift galaxies. Evo's paper with the bits to, and showing that, you know, there was an older stellar population there, probably a very large amount of build-up at an earlier time. This was a period where there was an awful lot of discussion going on about what are we seeing here. These are really bright. There's a huge number of them. They are massive as well. There's just so many galaxies there, massive galaxies, too many. What was going on? All these questions about whether the luminosity folded into mass in the same way that we've typically done at earlier redshifts. Just comments here about, even we got to the point of, as you've seen, comments about whether lambda CDM was in trouble. But we knew that we were facing some calibration issues here. The photo-Zs were probably or possibly wrong as well. It was very early days in this process. And there was a feeling that there's been a big move to get out data, get out results, and that some of the photo-Z samples were probably problematic, that the data was not really deep enough to be used for what a lot of folks were trying to do. The calibrations we knew were not adequate. We didn't have very good filters in the blue and a great deal of depth, and that's crucial for the null tests that you do with below Lyman alpha. And so the templates themselves, we were worried about those as well. It was interesting, the Nadeau paper, that this was on the ZF-17 galaxies that Donna and others have discussed. There was a solution for redshift 5 with very low probability. As it turned out, when a redshift was attained, it actually was at 5. So the templates were an issue as well there, as well as the calibration problems. But in the end, these two galaxies, these first two, turned out to be real and at high redshift. The spectroscopic redshift from the very highest one brought it down a little bit, as did many of them, in fact, changed their redshifts over time. So one of the things that I think helped a lot in understanding what was going on here was when Richard started to put together an analysis of the photo-Z results and to look at all the results from these three fields and some others. And this was worrying. So when you looked at the typical overlap between candidate lists and the earliest analyses were only 10 to 20%. This leaves you feeling that we're not doing a good job collectively on getting good samples of high redshift galaxies. So Richard started out trying to do this in a very conservative way. Arcane also did a similar very conservative analysis and looked at putting the photo-Z objects into different samples here: robust, solid, and possible. And interestingly, and that was based on the probability of falling in each of these groups from looking at the fits. But when you looked independently at them, robust, if there were, had 90% had two or more actual detections. But when you got to the solid sample, you were down to only 26, and the possible was only 12. So an indication of just some of the challenges there. What really clinched it for me was this figure. So looking at the SFRD versus redshift and seeing that the possible sample was just way out of bed with any likely reasonable development or change in the SFRD at early times. Solid, even so, was very unlikely. So this is circumstantial, but very indicative that we had a problem with our photometric redshifts. So the majority of the early photometric redshifts, very broadly in samples of there's several hundred, are probably not correct, was the end result of this discussion. And so in the end, I think it was very clear, and we know this too, of course, we've been working in this area, we need these spectroscopic redshifts to confirm things. But also it's just a warning that we really do need to be conservative and use data with good signal to noise for doing photometric redshifts and good blue data as well to define that break. And so I think now as we look at the samples, they are definitely improving. The photometric redshifts tend to overstate the redshift slightly as we look at these because when we look at the spectroscopic redshifts, but with a good sample it appears that it's a reasonably reliable technique, but it always needs to be treated with some skepticism. So the power of JWST for its spectroscopy, I think, came home to us when we saw these results from JADES. And so this was late in 22, and Brandt and Curtis Lake papers were instrumental in giving us a lot more insights into what was going on with these galaxies. Interestingly, this is sort of an interesting aside. I have to spend just a moment on this one. So this galaxy here in the Hubble Ultra Deep Field in the XCF turns out to be the highest redshift galaxy found by Hubble and Spitzer, and it had a very checkered history. Richard found this in the HUDF-09 data in 2010 and said it's a 2010 redshift 10 galaxy. We wrote a Nature paper published in Nature. Was wrong, like a lot of Nature papers often are. Subsequently, when the HUDF-12 data came in, and it turned out to be, it couldn't be a 10, it could be a 12. But then we went to look with the GRISM and with Gabe Brammer as well on this now, and we felt in the end that it was most likely to be a low redshift contaminant. So it sat that way for a long time until Richard and then Brandt last year, both independently, realized that, yep, it's in the JWST data and it's around 12. And then there was a spectroscopic redshift, which puts it at 11.6. So this is the highest redshift galaxy that Hubble ever discovered, and it was just an amusing story. So now we're starting to see some really great samples. So the JADES data is coming out and lots of redshifts. Clearly, we have very few spectroscopic redshifts in this range above redshift 10, where there are lots of questions about what is going on here with galaxies. But folks are working that, and that's going to come, a lot of that data. The primer data is wrapping up, and this is large area data fields with both MIRI and NIRCam imaging with lots of filters. So this is a data set that also is going to be very valuable, of course, public as well. And so now we're at the point of asking, so what is going on in the first, this early period? So I think that using GNZ11 as a pathfinder is a very interesting way to do this. This is a number of people have been looking at this. This was the galaxy that was originally found again by Richard in 2010, and with NICMOS data, and then with Wide Field Camera 3 data found by Pascal, and then a GRISM confirmed that it was around a redshift 11. And this is interesting. It sits in an early period. Planck tells us that there's very little reionization before redshift 10. And so here we have this sort of pathfinder galaxy from Hubble. It was really bright, unusual galaxy that we didn't know what it really meant and how common it was. JWST, of course, has revealed that these are quite common with the attendant. Let me see, did I jump? Yeah, I went the wrong way. So we now have JWST data on this, and quite a bit. So we have some imaging. We have this amazing spectrum, 20 hours. Here's a galaxy at redshift 11 with lots of metal lines, significant enhanced metal enrichment, 440 million years. And here's the old spectrum from Hubble So the difference, 8 hours, 20 hours, but the difference is just out of this world. So really showing how amazing Hubble is, JWST is. See Lyman Alpha in this at such an early time. Okay. I may have to jump some stuff here. Let me just finish this one up, I think. So the other aspect of this is that there's a potential detection of a population 3 component at large radii in this. This is an interesting aspect of this because it may help us understand what's going on in these galaxies if the stellar population is very different, if it's top-heavy. And so the masses are not as large as we might suspect. So, but it's a weak detection, and there's lots of questions about this. But we're at that stage now where we're looking at some of the pointers that are available to us. The second one is black holes are turning up. AGN in this galaxy, in all likelihood, there isn't a broad line spectrum from this one, but the spectral properties suggest it's AGN and star formation. So AGNs are turning up and seeing as much more common, I think, than we expected. So this is, I think, one way of trying to understand how we may have a way of getting out of this little box that we're in with at high redshift, is that we would not interpret directly those very high luminosities as very high masses. But it's totally open question at the moment. And so we're looking at, I'm looking at the discussion this week to give us much more insight. I just want to jump into just a couple of things here. The spectroscopic capability of Webb is, I think, where it's going to really make its scientific impact. The imaging is great. Hubble has been a great imaging telescope, but the spectroscopy on Webb is an immensely powerful capability. It will take some time to get a lot of the data here, but these GRISM images are incredibly powerful, 2 hours, and very low flux levels, very high quality data, 1600 resolution. This is powerful. So anyway, let me just jump over these things. Dark galaxies, AGNs. I want to flick over this because I want to go to, let me go to, thought you could type in this. No, it doesn't. Okay, I'm going to jump down, just go through this. So I just want to emphasize this again. I think that Planck is very interesting because these data, even with a new analysis in 21, indicates the optical depth at high redshift is very small. And so one of the constraints that we want to keep in mind when we're looking at the results out here is this, that there's can't be too much UV ionizing flux before redshift 10, 11, 12. And so I think this is a very powerful result. Okay, so let me just jump to this. So spectroscopy is crucial here. Bright, not massive necessarily, and I'll be interested to hear more discussion this week. Black holes, I think, are more prevalent. They're going to contribute to the light, and so they pose a different problem, early time black holes, and the top-heavy populations. And so I don't think, there's obviously been discussion about lambda CDM. I don't see any need for going there at this point in time. We don't understand enough about the galaxies themselves to take that huge step. And so Webb is really realizing its science capabilities here. It's huge data sets that are coming up. I'm sure we'll get to hear a lot about that this week. But also, I'm always struck by Webb is such a cultural icon these days that things pop up everywhere. This turned up, it was posted from Salem, Massachusetts during Halloween last year. She dressed up in this amazing costume. Somebody commented, it looks like we had a sun shield deployment challenge there, but it was just incredible to see this and to hear and find the interest in Webb, as in Hubble, but I think even more so, which is great for us as a community and for doing our future projects as well. So thank you very much.
Thank you, Garth. So we may have time for one quick question. And
yeah.
Meanwhile, can our next speaker coming up to setting up?
I'm sure you have lots of quick questions, Brad.
No, well, I mean, one thing I think you're uniquely qualified to answer. What was the one thing that people wanted to have in JWST at the very beginning when you all were planning it that you think we really should have kept but didn't? Was there anything?
I think, you're talking now about the mission itself and its capability. I think this exceeds everything that we wanted at that point. The only thing is that we're smaller, and we were talking 8 to 10 meters as being the ideal size. And, you'd love to just have a bigger telescope. But everything else, I mean, the temperature's lower, the instrument and detector performance is far beyond what we ever could have conceived in that point. The stability, the optical quality, it's everything pretty much. So I had to go back then and somebody said, here's what we're going to give you. Thank you.